On the preceding slide, we wrote Henry's law in the form that resembles Raoult's law. That is, by expressing the partial pressure of the solute in terms of the mole fraction of solute in solution. Henry's constant, K prime sub h, is therefore defined as the ratio of a pressure over a mole fraction, and has units of pressure. Henry's law can actually be written in as many different ways as there are ways to specify the concentration of a solute in solution. So if we choose to use the molarity as a measure of the concentration of solute B in solution, then Henry's law can be written as molarity of B is equal to K sub H times the partial vapor pressure of B, where Henry's constant, K sub H, has units of moles per cubic meter per kilopascal. Values of Henry's constants are given for a number of gases dissolved in water at 25 degrees Celsius in these units in the table on the right-hand side. Regardless of which Henry's constant is given, you should remember that Henry's constant is a characteristic property of the solvent-solute pair and depends on temperature. You should also remember that if you know 1 Henry's constant for a given solvent-solute pair, you can easily derive the Henry's constants applicable for other measures of solute concentration. For example, dividing the second equation by the first leads to K sub H equal to the molarity of B divided by the product of the mole fraction of B in solution and Henry's constant K prime sub H. Now you may ask, given a value of Henry's constant, which Henry's law should we use? The answer is simple. We must look at the units given for the Henry's constant. If the units of Henry's constant are units of pressure, then Henry's law should be expressed as Pb equal K prime sub H times XBL. If the units of Henry's constants are units of pressure over units of molarity, then Henry's law is expressed as molarity of B equal to K sub H times partial pressure of B. As an exercise, you should think about how we would write Henry's law if the units of Henry's constant were units of molality divided by units of pressure. Now, on the preceding slide, we used Henry's law expressed in terms of the solute mole fraction to describe the chemical potential of the solute in a very dilute solution. We can now do the same using Henry's law expressed in terms of the solute molarity. Rearranging the above equation, we get molarity of B equal to the product of K sub H, K prime sub H, and XBL, or XBL equal to molarity of B divided by the product of K sub H and K prime sub H. Then we use this expression of XBL in the expression of the chemical potential of the solute B in a very dilute solution derived on the preceding slide and obtain mu B in the liquid or solution phase equal to mu B star liquid plus RT times the natural log of XBL, mu B liquid in solution phase or liquid equal to mu B star liquid plus RT times the natural log of the molarity of B minus the natural log of the product K sub H times K prime sub H. Note that we have included a term C standard in the argument of each logarithm term to ensure that these arguments are unitless, as they should be. The standard molarity is defined as 1 mole per cubic decimeter or 1 mole per liter. We combine the first two constants on the right-hand side of the expression of the chemical potential to define a new standard chemical potential applicable in the limit of ideal dilute solution at the hypothetical standard concentration of 1 mole per liter. So we can finally write mu B liquid equal mu B liquid standard plus RT times the natural log of the ratio of molarity of B divided by the standard concentration. Note that when the molarity of B is equal to 1 mole per liter, then indeed mu BL is equal to mu BL standard. Henry's law is particularly useful in the life sciences as oxygen and carbon dioxide gases are present, dissolved in our body in very small concentration. So let us look at a specific example of calculation involving Henry's law. The problem we tackle here consists in the determination of the minimum partial pressure of oxygen required to support aerobic life, given that the minimum concentration of O2 dissolved in cells is about 4 mg per cubic decimeter. In the literature, we find that Henry's constant for oxygen in water at 25 degrees Celsius exhibits a value of 1.30 times 10 to the minus 2 moles per meter cube per kilopascal. From the units given for Henry's constant, we conclude that Henry's law must be written as molarity of O2 equal Henry's constant times the partial pressure of oxygen. We know the minimum concentration of oxygen as 4 mg oxygen per cubic decimeter of solution. So, dividing by the molar mass of oxygen, 32 grams per mole, we calculate the minimum molarity of oxygen as 0.125 moles per cubic meter. Hence, the minimum partial pressure of O2 is equal to the minimum molarity of O2 divided by Henry's constant, K sub H. Or P oxygen equals 0.125 mole per cubic meter divided by 0.0130 mole per cubic meter per kilopascal. P oxygen is equal to 9.6 kilopascal. This minimum oxygen partial pressure can be compared to the partial pressure of oxygen in air. Indeed, using Dalton's law, we calculate the partial pressure of oxygen in air by multiplying the mole fraction of oxygen in air, or 0.21, by the atmospheric pressure, 1 atmosphere, or 101.325 Pascal, or 101.325 kilopascal. So we can see that the amount of oxygen present in our atmosphere is more than twice as large as needed to sustain aerobic life in streams.